alaikum wa rahmatullahi wa barakatuh. Hi everyone, nice to meet you all. Today, inshallah, we will start to complete the different types of isomerism. In the last videos, we have finished structural isomerism with its different types like chain isomerism, like functional isomerism, like positional isomerism. If you want to memorize it, you can come back to the video. I will keep its link on the description box. We have finished also geometrical isomerism as the first type of stereoisomerism. I will keep its link down. Now we will start to complete together in optical isomerism. We will start to understand what is the meaning of optical isomerism. Optical isomerism is one of the different types of stereoisomerism. The first type is geometrical isomerism and the second type is optical isomerism. Optical isomerism, we can find it in the chemical compounds which contain chiral carbon atom. What's the meaning of chiral carbon atom? It is the chiral carbon atom. Any carbon atom surrounded by 4 different atoms or 4 different groups. So you must have 4 different atoms or 4 different groups to say that we have chiral carbon atom. In the chemical compounds, we can write it at C star. Just add star next to your carbon atom. So we can say we have chiral carbon atom. In our compounds, we will have 2 mirror images. We can say we have non-superimpossible mixture. How can we have non-superimpossible mixture? Exactly, it is like your hands. Your hands are exactly the same shape. They are mirror image. One of them right and the other one is left. So we can say they are optical isomers. We can say they are identical, but they are still non-superimpossible. If we start to move them, it is impossible to stack or to join all the parts of my hands together. So we can say they are optical isomers. In our picture, we have one compound. This compound is one of optical compounds. Its mirror image exactly is the same, but start to draw with mirror image. For example, this side you will draw with in the front side, and the far side you will draw with on the other far. Take care, in the case for organic compounds, we have 3D compounds. 3D compounds means we have carbon atom attached with another atoms or groups. We have atoms on the same plane. We have atoms from behind. We have atoms from front. So we have 3D structure. It is the definition of the non-superimpossible. We have mirror image, but it is impossible to stack from exactly one of the top to the other. It's exactly like your right hand and your left hand. They are optical mirror. Let's complete together at how can we know we have optically active compound. If you are working inside your lab and you have unknown chemical compound, exactly if you have unknown chemical compound, you won't know if you have chiral carbon atom or if you don't have chiral carbon atom. So how can we know practically that we have optical active compound or optically inactive compound? We can measure the optical activity of our compound by using polarimeter. Polarimeter is used to measure the optical activity of compounds. Inside the lab, it is the structure of polarimeter. In our polarimeter, we have a source of light, but our source of light will produce light with different wavelengths. So at first we will add filter. Why we will add filter? To have only monochromatic light, to have a light with only one wavelength. So our monochromatic light will start to transfer through our sample, will transfer through our chemical compound. By transferring the light through our compound, we will start to make rotation for our light. If the rotation to the right, so we have dextrorotatory. If the rotation to the left, we have levorotatory. We may have racemic mixture. We will know what's the meaning of the racemic mixture in the next slides. So we will start to analyze the rotation of the light. The rotation of the light means we have optically active compound. If we have no rotation, of course we have compound is inoptically active or not active. Okay, so at first we have two types of optical activity. We have dextrorotatory plus or D. Dextrorotatory plus or D, it rotates the plane of the polarized light to the right. We can say it rotates the polarized light with clockwise direction. We can have levorotatory or negative or L as abbreviation. So it will rotate the plane of the polarized light to the left. So we can say it is rotates the polarized light with anti-clockwise direction. So it is the meaning of dextrorotatory and levorotatory definition. Now let's transfer to the next slide, racemic mixture. Racemic mixture, we have mixture of two optically active compounds. One of them is dextrorotatory. One of them can rotate the polarized light to the right. The other one can rotate the polarized light to the left. But they are with equal percentage. But they are with equal value. 50%, 50%. So if I have the plane of polarized light, at first I will start to rotate it to the right. Then I will start to rotate it to the left. So the plane of your polarized light, will it change it? Of course no. So the racemic mixture is like our mixture. We have mixture of two mirror images. The first one is dextrorotatory, rotates the plane of the polarized light to the right by 13.5 degree rotation. The other one is levorotatory. The other one is racemic mixture, can rotate the polarized light to the left. It's the negative, so it will rotate the polarized light by minus 13.5. So we have equal quantities of dextrorotatory and levorotatory. We have equal quantity of D and L, positive and negative. Of course, as a mixture, we will have optically inactive compounds. We will have racemic mixture. The mixture may have different melting point and different boiling point. So we can say in our example of hydroxyl propanoic acid, lactic acid, we have one chiral center. But in our chiral center, we have mixture of dextrorotatory and levorotatory with equal quantities. As we have equal quantities in our mixture, we will have racemic mixture. Now we will transfer to one of the important topics. How can we know the chiral carbon atoms in cyclic compounds? This question is repeated a lot, especially or exactly for AS level students. How can you know the chiral carbon atom in cyclic compounds? We have specific rules. At first, you must start to cancel any carbon atom contains double bond, because we need the chiral carbon atom surrounded by 4 different atoms or groups. So at first, cancel any carbon atom with double bond. The next one, cancel any carbon atom attached to 2 atoms only, or make 2 bonds only. Why we must cancel it? Because of course it has 2 hydrogen atoms, so it will cancel the optical activity. Number 3, we are looking for any carbon atom attached with 3 different bonds. After knowing any carbon atom attached with 3 different bonds, just have a general look if we have optical carbon atom or the optical inactive carbon atom. Let's have some examples together. At first, we have our compound. Our carbon atoms are 1, 2, 3, 4, 5. We have 5 carbon atoms. We will start to cancel the optically inactive carbon atoms. First one is attached by double bond. Cancel it. Second one, double bond. Cancel it. Third one attached with 2 carbon atoms only, so we have 2 hydrogen atoms. Cancel it. Last one is the same, attached to 2 carbon atoms. Cancel it. The last one, we have carbon atom attached to 2 carbon atoms and 1 hydroxyl group, and we have another hydrogen atom. So it is attached to 4 different atoms or groups. So we can say that we have chiral carbon atom, we have C star. The next one. In our compound, we have 1, 2, 3, 4, 5. But take care, we have 2 methyl group. So we have 6 and 7. At first, start with the methyl group. We have carbon atom attached to 3 hydrogen atoms. Of course, it is optically inactive. Cancel. Next one, of course, optically inactive. Cancel. Third one, attached to 2 carbon atoms. So cancel. Attached to 2 carbon atoms. Cancel. Cancel. Attached to 2 carbon atoms only. We have 1 carbon atom attached to, at first, carbon, methyl, and we have another hydrogen. It is optically active. C star. The other one, it is attached to 4 different groups. So we have chiral carbon atom. We will have extra complex compounds. At first, we have the following compounds. At first, we start to know what is the carbon atoms in our compounds. At first, we have carbon atom attached to hydroxyl and 2 carbon atoms and hydrogen. We have optically active carbon atom. This attached to 2 carbon atoms, cancel. Attached to 2 carbon atoms, cancel. Cancel. We have carbon atom attached to 1, 2 methyl group and another carbon atom. Of course, it is optically active. The other one, we have double bond. We have optically inactive carbon atom. The other one, 1, 2, 3, 4, optically active. The other one, 1, 2, 3, 4, optically active. This one, optically inactive. Why? Because we have 2 bonds on. We will transfer to 5. 5, of course, is optically active. 6, optically active. 7 is the same. So just follow our rules to know which carbon atom is chiral carbon atom. The last example is exactly the same. Okay? Take care. In the first one, this carbon atom is chiral or inchiral or inactive? It is inactive carbon atom. Why? Because we have two methyl group. We have two CH3 group. So it is a trick for you. Okay? Next one, no, it is optically active. This one, it is optically active. This one, optically active. In the next compound, 1, of course, is optically active. 2, optically active. 3, 4, 5, 6, 7, 8, 9 is optically active. Any other carbon atom is optically inactive. Why? You will find it is attached in double bond. You will find it attached to only 2 carbon atoms. You will find that it is joined to 2 similar groups. So, of course, we have an optical active compound. We will transfer to the last information in our video today. At first, you must know that optically active compounds are widely used in pharmaceutical application. For example, the ibuprofen is one of anti-inflammatory medicines. It is widely used for treating in our daily life. Ibuprofen is one of pharmaceutically optically active compounds. In the compound in industry, we have a racemic mixture of dextrorotatory and mixture of levorotatory. In your compound, you will find that one part is active ingredients. The other part is non-harmful. So it is exactly accepted to have a racemic mixture of our compound, because the part which is optically active and active ingredients as a medicine will be used. The other part is non-harmful, so we can add it like starch in pharmacy. The same in the case of our optical active isomer. It is one of the chemical compounds which used in pharmacy. Thalidomide is one of the chemical compounds widely used before in the case of pharmaceutical compounds. It is highly polarized compound. It is used in pharmaceutical compounds. Thalidomide contains a chiral carbon atom, so it is a chiral molecule, and it can exist as 2 enantiomers as our compound. Thalidomide was invented in 1960, and it was used for treating anxiety and early vomiting or early sickness in the pregnant women. When they start to use it, after a period of time, we have a problem in the case of our newborn babies. We have percentage of newborn babies have the problems in formation. So we have these deformities and missing limbs. So they start to study thalidomide again. Thalidomide compound, we exactly in industry we must use one isomer. But in the industry, in the factory, by mistake, the other isomer is added to the mixture. The other isomer, when added to the mixture in the human body, it is converted into one of the compounds which can make problems for the newborn babies. So it is turned to only one of enantiomers. It is the structure on the right. Was effective and safe. So the first one is effective and safe, but the other one, it is harmful So in the mixture in industry, we have a mixture of the two isomers. The drug was banned and we stopped any use for thalidomide for pregnant women. And we stopped to use it. By this information, we have finished our video today. I hope that you understand what is the meaning of optical isomerism, different types of optical isomerism, uses of isomerism in industry, how can we know that we have optical isomerism in cyclic compounds. Thanks for watching our video today. I hope that if you have any question in our video, just send a comment for me and I will of course answer your question. Thanks for watching. See you later and Assalamu alaikum wa rahmatullah wa barakatuh.